Welcome to today's webinar, Testing Adaptive Antenna Arrays for GNSS Receivers, brought to you by GPS World Magazine and our sponsor of the event, Rohde Schwarz. Before we get started, I want to let you know that today's webinar will be recorded. You are currently in a listen-only mode. A recording of this webinar will be posted to gpsworld.com/webinars and will also be emailed to you tomorrow. At this time, I'd like to acquaint you with the ways in which you can participate during today's presentation. Please notice the Q&A panel at the left-hand side of your console. If you have a question, type it in the panel's text box, then click Submit to place your question in queue. We encourage you to ask and enter any questions you may have for our speakers during the presentation. Questions submitted during registration have already gone to our panelists and may be addressed during the presentation. If you experience any technical difficulties during today's event, you may use the same Q&A panel on your screen to submit your issue, and I or Technical Support Specialist Marie Emmerich will personally assist you. You may learn more about our speakers by viewing their photo, bio, and email address in the panel located on the upper left-hand side of your console. If you are logged into your social media accounts, you can share the webinar's title, description, and URL with your friends or colleagues using the Share This widget you'll see in the bottom left corner of the screen. Finally, at the bottom right of the console, you will find a link to visit the Rohde Schwarz website along with GPS World website. I'm Aurora Harris, Content Marketing Producer for GPS World Magazine, and I will be your moderator for today's webinar. Now, I'd like to introduce today's presenters. Today, we will be hearing from Marcus Ersigler, Product Manager of GNSS of Rohde Schwarz. Marcus joined Rohde Schwarz in 2012 and is involved in product planning, product management, and marketing activities. We will also be hearing from Sebastian Kelwas, Application Engineer of Rohde Schwarz. Sebastian joined Rohde Schwarz in 2018 and is involved in application development and application support activities. At this time, I'll turn the presentation over to our presenters. Take it away.
Hello, welcome, and thank you for tuning in to this webinar on testing adaptive antenna arrays for GNSS receivers. My name is Marcus Irsigler. I'm a product manager for signal generators. And here with me in the studio is Sebastian Kelwas. He is application engineer and will present the second part of this webinar. Hello, Sebastian.
Hi, Marcus.
So let's see what we have prepared for you. We have divided the webinar into three parts. In the first part, we will talk about different types of signal degradation or threats that must be expected when using GNSS. And we will discuss how these threats can be detected and mitigated with receiver internal methods. And one of these threat detection and mitigation method is to use adaptive antenna arrays. And in the second part of this webinar, we will focus on these systems and look into the corresponding signal processing techniques. And then in the final part, we will show you how you can test multi-antenna GNSS receivers against various types of threats using signal generators from Rohde Schwarz. And based on very practical test cases and test scenarios, you will hopefully get a good idea about the various simulation capabilities our instruments are able to cover. So let's start off with a first overview of different threats and error sources that can degrade GNSS signals and affect the positioning and navigation performance of GNSS receivers. Signal degradation effects of any type can basically occur anywhere on the way from the GNSS satellite to the user. They can be caused by the transmitting satellite itself, typically in the form of hardware malfunctions, and this is typically referred to as evil waveforms. They can also occur along the signal path in the form of ionospheric and tropospheric errors or scintillation effects, or they can be a result of the conditions in the vicinity of the receiver. And this includes jamming, spoofing, RF interference caused by other signals, but also signal obscuration and multipath caused by buildings or trees. And all these effects or threats that can occur in the user environment can be considered as man-made threats. So let's now have a closer look at these man-made threats, starting with interference signals. Interference can either be intentional or unintentional. Intentional interference is called jamming and can be divided into brute force jamming, where the receiver is completely unable to acquire and track the GNSS signals, and systematic jamming, which is also called smart jamming or intelligent jamming, where the receiver is still able to track the signals but unable to compute a position solution. Typical interferer signals of this kind include CW interferers, broadband noise, frequency sweeps, or pulsed interference signals. And these signals are typically used by so-called personal privacy devices, PPD. Then we have the category of unintentional interference that include signal obstruction by buildings or trees. They include multipath effects caused by reflections from buildings, from the ground, or also from trees, and interference caused by other communication signals we are using every day, like LTE, for example. Then we have spoofing, which is a very special type of interference. And that can be described as a method to manipulate the receiver's position and timing information so that the navigation information is still valid but incorrect. There are basically two different ways to perform a spoofing attack. It can be done by either generating a broadcast and broadcasting a fake GNSS signal. In this case, a signal generator is needed to perform the attack, or by rebroadcasting a GNSS signal. This is called meaconing and requires either a GNSS repeater or a record replay system. And what you see here on the bottom of this slide is how the receiver operation is affected by such threats. In case of a successful jamming attack, the receiver is at least unable to provide a position solution. But in many cases, and this is especially when we talk about brute force jamming, the receiver will even be unable to receive any GNSS signals at all. Then unintentional interference typically degrades the positioning performance because less satellites are in view. This is when we talk about signal obstruction, or because signal reflections cause ranging errors. This is when we talk about multipath, or because the C/N0 of the GNSS signals is lower than normal. And this is when we talk about interference by other communication signals. And in case of spoofing, the receiver typically still works, but it works incorrectly and unreliably. Among all these threats, jamming and spoofing can probably be considered as the most serious threat, as they compromise the availability, the reliability, the accuracy, and also the integrity of GNSS-based navigation. And as we can see on the next slide, these threats are not just theoretical threats. So this is just a small selection of headlines from navigation magazines and from the internet covering the jamming and spoofing topic. These headlines indicate that jamming and spoofing incidents and attacks do not occur occasionally, but very frequently. As an example, here in 2020 alone, several thousand jamming and spoofing incidents have been reported. And apart from the pure technical aspects, the problem has also been recognized as an economic risk, as we can see here when we're reading this headline here: manipulated GPS data becomes $1 billion risk for logistics. So this already leads us to the question how such threats can be detected and even mitigated, and this is what we want to discuss next. There are, in fact, a number of different ways to detect and mitigate GNSS threats. They are listed here on this slide, and I would like to go over at least some of these approaches. So let's start with spectrum monitoring. With spectrum monitoring techniques, it is basically possible to detect signal malfunctions caused by evil waveforms, for example, or to detect interfering signals like jammers, basically by simply looking at the spectrum of the received GNSS signals. Then we have C/0 monitoring that can also be used to detect jammers. The reason is that jamming leads to either a decrease in the observed C/0 or, and this is the more typical case, completely makes it impossible for the receiver to track the signals. C/0 monitoring can also be used to detect multipath because multipath typically leads to periodical C/0 variations. The next method is to analyze different GNSS observables, for example, single differences, double differences, or code-minus-carrier data. These observables can be used to detect multipath because also in this case, multipath will cause periodic variations of the data series. Then we have techniques like RAIM, Receiver Autonomous Integrity Monitoring, and in very simple terms, this technique is capable of detecting pseudo-range errors on GNSS signals and to exclude the affected satellites from the positioning solution. Such errors could be caused by multipath or also by evil waveforms. A very interesting interference detection method is the use of multicorrelator techniques. This technique is used during the correlation process in the GNSS receiver to sample the signal's correlation function and to detect distortion in the correlation functions. Such distortions typically occur in the presence of multipath, evil waveforms, or also during a spoofing attack. And here in this diagram, you can see how multipath affects the shape of the correlation function. And based on several correlators that can be used to sample the correlation function here, it is possible to detect the corresponding signal distortions. On the right-hand side here, we have listed some additional techniques for interference mitigation, like frequency domain adaptive filtering, pulse blanking, and optimized antenna reception pattern. And one example of using an optimized antenna reception pattern are choke ring antennas. They consist of a number of conductive concentric rings, and they are able to reject signals coming from either below the horizon or from very low elevation angles. And such antennas are typically used to reject ground multipath as well as multipath signals coming from low elevation angles. Here on this slide, you see the same list of interference detection and mitigation techniques, but now with an indication where exactly in the GNSS signal processing chain these techniques are typically used. So we have a basic GNSS receiver architecture with an active antenna, which is the green part here. This is where the signals are received, amplified, and band limited. Then we have the receiver front end, the yellow or orange part here, where the signals are down converted, filtered, and where the analog to digital conversion takes place. And we finally have the digital signal processing part, this blue part here, where the signal conditioning, the acquisition, the tracking, and the PBT solution computations take place. And here in the lower part of this slide, you can see where exactly the different interference detection and mitigation techniques happen. For the remainder of this webinar, we will focus on using optimized antenna reception patterns for interference detection and mitigation. We have already heard about choke ring antennas as one possible implementation of this method, but a much more powerful and flexible way to detect and mitigate interfering signals is to use an antenna array instead of only one antenna. And this is exactly the topic of the next part of this webinar. And for this, I will now hand over to Sebastian.
Thank you, Markus. That's right. Adaptive antenna arrays indeed prove to be most effective against jamming and spoofing attacks. When using a set of antenna elements rather than a single antenna, it is possible to adaptively change the resulting antenna reception pattern. This can be used, for example, to introduce so-called null in the reception pattern that filters signals arriving from a certain direction. In this case, you can think of the antenna pattern as a spatial filter. In the absence of interference, the spatial diversity of an antenna array can be used to form beams towards satellites and thus to increase the quality of the received signal. In the second part of our webinar, we want to talk more about adaptive array processing techniques and typical receiver architectures. We will also have a look on some example algorithms. When using an adaptive antenna array with multiple elements, the resulting antenna reception pattern is formed by weighting the received signals on each antenna element, here called X, with a complex weight W. The weighting process is followed by a summation over all signals. The resulting signal is then fed to the next processing block. This can, for example, be a standard GNSS receiver with a single antenna port, or the tracking loop in a receive channel of an array receiver. In most applications, the complex weights are calculated based on predefined optimization criteria, either at the pre-correlation stage or at the post-correlation stage. We will have a look on both use cases in this webinar. An example for pre-correlation techniques is to form the reception such that the received power, here the power of the signal Y, is minimized. This results in an antenna reception pattern with reception nulls in the direction of strong signal sources, such as interferers. So the influence of the strong signals is reduced as much as possible. An example for post-correlation array signal processing is the maximization of the signal to interference and noise ratio of the GNSS signals. This results in beams towards the satellites in view. In literature, adaptive antenna arrays are often referred to as controlled reception pattern antennas or short SERPs, especially in the context of GNSS. A typical receiver architecture that employs pre-correlation techniques to improve its robustness against interference usually has an antenna array with 4 to 7 or even more antenna elements. The received signal on each antenna element is amplified and filtered, down-converted, and then sampled. After the analog to digital conversion, complex weights are calculated here based on the individual signals and applied here. Since all useful GNSS signals are very low power and therefore buried in the thermal noise floor, the weight calculation is performed on dominant signals and well-observable signals, mostly interfering signals. By minimizing the received power, it is, for example, possible to remove these interference signals while the useful signals pass through. The sum signal, which is ideally interference-free, can then be fed into a standard GNSS receiver. A typical pre-correlation technique I already mentioned is the so-called power minimization. The assumption here is that all signals adding significantly to their total received power are interfering signals. As all GNSS signals are buried in the noise floor, this is usually a valid assumption. By choosing the weights such that the received power is minimized, an antenna pattern is formed which has reception nulls in the direction of interference sources. However, simply minimizing the received power would lead to the trivial solution of all weights being equal to 0. By multiplying the signal on each antenna element with 0, the power would definitely be minimized. But of course, there would not be an input signal for the GNSS receiver anymore. To avoid this solution, there is an additional constraint that the weight for the signal of antenna element 1 is equal to 1. This is formulated here. With this constraint, it is assured that the trivial solution is avoided and that there actually is an output signal after the weighting process. With this approach, it is possible to form n-1 nulls, where n is the number of antenna elements. So with a 4 antenna element array, for example, it is possible to form 3 reception nulls. So you can basically cancel 3 interferers from different directions. 1 degree of freedom is consumed for the constraint on the reference element that is needed to avoid the trivial solution. In this case, GNSS signals that arrive from the same direction as the jammer that is nulled are also nulled. So this might reduce the number of satellites in view. Instead of a single constraint on the reference element, it is also possible to form multiple constraints for the optimization. One example would be to minimize the receive power based on the constraint that the gain in the look direction of a number of GNSS satellites is equal to 1. So what does that mean? That means we put a certain direction in the form of a steering vector into the optimization and say that in this direction the gain pattern of the antenna array, so the resulting reception pattern, shall be equal to 1. By constraining the gain, the resulting antenna pattern can be optimized for both interference suppression as well as GNSS signal reception. The plane power minimization, which I introduced on the previous slide, is a so-called blind technique. Blind because it does not require any a priori information on the jammer, the GNSS satellites, or the receiver. Opposed to that, this approach requires knowledge of the GNSS satellite positions in the form of ephemeris data, as well as the receiver attitude to formulate the look direction to a certain satellite. A disadvantage of this approach, especially with antenna arrays with a small number of elements, is that each constraint decreases the number of interfering signals that can be nulled. Another approach is to perform adaptive array signal processing on the GNSS signals after correlation. Here, the GNSS signals are already well above the noise floor and can be used for weight computation. In a typical architecture, the signal of each antenna element is fed to each receives channel. You can see that here, the signal of antenna 1 is routed to all channels. So is the signal of antenna 2 up to the signal of antenna n. So in each channel, here, there are correlators in parallel equal to the number of antenna elements. So with the output of these correlators, we have the signal of a single satellite for each antenna element. These signals can now be used to calculate weights for the dedicated channel. It has to be noted here that the weights usually differ in each receive channel. So we get a different reception pattern in each receive channel, and the number of different patterns is only limited by the number of parallel channels. Whereas this approach is much more complex and computationally expensive than the pre-correlation technique, the architecture provides the possibility to form a separate beam on each satellite in view. An example for a post-correlation technique is the so-called minimum mean squared error beamforming. Here, the mean squared error of the received signal is minimized with regards to a reference signal. A reference signal that is already available in every GNSS receiver is the local code replica, so the local replica of the PRN sequence of a single satellite. This signal is needed for correlation anyway, so it can easily be used in the weight computation process as well. With this technique, a separate beam can be formed independently for each space vehicle that is tracked by the receiver. As I said, only limited by the number of parallel receive channels in the GNSS receiver. However, using the local replica of the PRN sequence as a reference also introduces the disadvantage that it's susceptible to multipath-induced errors. An echo resulting from multipath propagation is basically only a delayed version of the line-of-sight signal, which still contains the PRN sequence and consequently also matches with the reference signal. In addition to the techniques to use adaptive antenna arrays that we just discussed, there are other benefits which are illustrated here. We have talked about the beamforming towards space vehicles, and we have talked about the RF interference mitigation. Further applications for adaptive antenna arrays are, for example, the direction of arrival estimation of interference sources. This can be used to actually locate the source of unintended or intended interference. Other techniques are the attitude determination of the receiver platform by means of multiple antennas, as well as multipath detection and mitigation, or spoofing detection and, of course, mitigation. As an example, a spoofing attack can be detected by estimating the direction of arrival of all satellite signals in view. In the absence of a spoofer, the estimated direction of arrival should be first of all different for all satellites, and it should match the direction that can be calculated from the receiver attitude and the satellite ephemeris data. In case a spoofing attack is executed and the GNSS receiver actually falls for the spoofing attack and locks onto the spoofed signal, the estimated direction of arrival is identical for all satellite signals. It will be the direction of the spoofer. This way, a spoofing attack can be detected, and by introducing a reception null into the direction of the spoofer, the attack can also be mitigated. So you see, adaptive antenna array processing can be very versatile and brings a lot of benefits, especially when used in combination with GNSS receivers. In the final part of this webinar, we want to talk about test requirements and solutions for adaptive antenna arrays. We will have a look on typical test cases, and finally, I want to show some test results of a very basic nulling algorithm. In order to thoroughly test an adaptive antenna array on a GNSS receiver, the test environment has to fulfill some requirements. As the number of GNSS signals has largely grown in the past few years, it is essential to simulate multiple constellations on all common frequency bands in order to provide a realistic signal environment. Another important aspect for testing array receivers is the precise alignment in terms of amplitude, group delay, and phase at the antenna feed. To test the real performance of a nulling or beamforming algorithm, the test signals have to be as realistic as possible. That means, for instance, that the phase relation between the signals at the individual antennas has to be exactly according to the simulated scenario. Some factors that have an influence on the phase relation are the array geometry, the platform attitude, and the direction of arrival of the interfering signals. Residual phase errors of the test system directly translate into errors of the simulated direction, and thus lead to a biased evaluation of the receiver performance. Integration of realistic gain and phase radiation patterns is also a key requirement when testing adaptive antenna arrays to obtain meaningful results. As user requirements on the number of RF ports on the DUT tend to change over time, it is also quite helpful to have a scalable system architecture which can be expanded when necessary. And last but not least, the simulation of RF interference with a high geometry signal ratio and simulation of spoofing attacks shall be possible in a simple and intuitive way. Ideally, the scenario generation can be performed manually as well as automated. The Rohde and Schwarz test system for multi-antenna GNSS receivers is based on the SMW200A vector signal generator. With the integrated GNSS simulation software, the SMW can be turned into a fully fledged constellation simulator. The SMW200A can be equipped with 1 or 2 RF ports, and to test typical antenna array receivers with 4 or more antenna ports, multiple instruments can be coupled. Here you see a setup consisting of 4 two-path constellation simulators to test GNSS receivers with up to 8 antenna elements. The setup is scalable by simply adding or removing SMWs. The alignment process of this setup in terms of amplitude, group delay, and phase is automated using the Rohde and Schwarz RF ports alignment software. A vector network analyzer, which you see here at the bottom of the rack, can be used for all related measurements. Thanks to the modular concept, it is also possible to use subsets of simulators independently. For example, this setup can be divided into 2 test setups, and each test setup can then be used to test 2 4-antenna receivers in parallel. With the Rohde and Schwarz pulse sequencer software, it is very easy and intuitive for the user to create complex jamming scenarios. We will have a look on this in the example test cases later. This setup also allows for integrated multipath, spoofing, and jammer simulation. For the simulation of very high jamming to signal ratios, we recommend to use a separate RF output for each antenna element. So with this test setup, a very wide range of test cases can be covered, and on the following slides I want to give a few examples. The first test case I want to show is the simulation of an interference-free scenario. This is, for example, performed to evaluate new beamforming algorithms for attitude determination or just to set a reference. The receiver can be configured to follow any predefined trajectory, as you see here. Here, for example, I've selected an approach to Munich Airport, but any user-defined trajectory can be loaded as well. Within the graphical user interface, it is also possible to configure the antenna geometry. This includes the position as well as the attitude of each antenna element. And here you see, for example, an antenna array with 4 elements arranged in a star configuration. And it is possible to load gain and phase pattern for each element. Here on the right, you see the gain and phase pattern used in this configuration. And this, for example, is a pattern of a typical patch antenna. To make the simulation more realistic, we want to add some interference in the form of multipath echoes in the next test case. The SMW allows to define up to 9 echoes per satellite, and the settings can be individual for each satellite and also antenna. The individual configuration for each antenna element allows to simulate, for example, very close obstacles, which would lead to a different incident angle at each element. The echoes can be defined in terms of code phase drift, power offset, and most important for testing array receivers, initial carrier phase, the azimuth and elevation angle of arrival. Here in the third test case, you see the configuration for testing an adaptive antenna array receiver against a spoofing attack. Therefore, a second vehicle is configured with the same number of antenna elements as the first vehicle, as the real receiver. In a spoofing attack, all the GNSS signals, as they are simulated from a simulator or retransmitted in a weakening attack, arrive at the receiver from the same direction. So for the spoofed signals, the phase relation between the signals on each antenna element is identical for all satellites, irrespective of the actual satellite position. To simulate this phase relation, all antennas of the second vehicle are put into the same location. You see that here all offsets are 0. And the direction of arrival of the spoofing signal is simulated by setting a common phase offset for all the satellite signals that arrive on a single antenna element. The required phase offset can be calculated according to the antenna geometry, the receiver attitude, the frequency, is it L1, L2 or L5, and the spoofer direction. The last test case I want to discuss is a jamming scenario. With the Rohde Schwarz pulse sequencer software, this test is very easily configured. The interferer, you see it up here, can be placed on a 2D map via drag and drop. Here it is located at a bearing of 60 degrees and a distance of 5 kilometers from the receiver, and it is pointing to the receiver, to the GNSS receiver. The GNSS receiver has an antenna array that we already know from the previous test case. It has 4 elements in a star configuration. And here on the right, you see the envelope of the interfering signal. It is an intermittent CW signal centered at L1. And for the first 100 seconds of the simulation, it is switched off, and then it is turned on for 10 seconds. The scenario can simply be started by calculating the signals in the software and clicking the play button. Then the signals are automatically loaded to the generator setup, and the replay is started either automatically or on a trigger event. For this last test case, I want to show some test results of a very basic nulling algorithm. You see here on the left the carrier to noise density ratio over time, and on the right the number of tracked space vehicles over time for a single antenna on the top and for an adaptive antenna array receiver on the bottom. The duration of the jamming attack is marked by the red area here. As you see, before the jamming attack, both receivers have a stable tracking of 4 or 5 and then later 10 satellites with a carrier to noise density ratio of approximately 40 dBHz. During and after the jamming attack, the single antenna receiver starts to lose most satellites. It goes down to about 4 satellites, and it takes almost a minute until it can reacquire the signals and has a stable tracking again of about 40 dBHz. Opposed to that, the array receiver does not lose track of a single satellite. Actually, it can acquire another satellite shortly after the jamming attack. And also the carrier to noise density ratio changes only slightly during the jamming attack. It increases for about 2 dB for some satellites and decreases by the same amount for other satellites. And this variation results from the shaping of the antenna pattern and the accompanying change of gain in the direction of the satellites. So you see, a simple nulling algorithm already provides good protection against the jamming attack. With these results, I want to conclude my part on adaptive antenna arrays and how to test them. I will now hand back to Markus for a short summary.
Thank you, Sebastian. We have almost reached the end of the webinar now, and I would like to use the remaining time to summarize what we have discussed so far. So whenever your task is to simulate unintentional interference, multipath, jamming, or spoofing attacks to test your adaptive antenna arrays, we have an excellent and scalable solution which is based on our high-end GNSS simulator, the SMW200A. As you have already heard, one SMW is able to generate signals for 2 antenna elements. And depending on the number of antenna elements in your antenna array, you can combine several instruments to form an integrated test system that you can see again here on this slide. So scalability is therefore one major benefit of our solution. And in addition to that, we offer automated calibration for these systems. And finally, the system supports comprehensive and realistic multi-constellation and multi-frequency GNSS simulation with the capability of simulating complex multipath scenarios as well as jamming and spoofing attacks. So this concludes our webinar on how to test adaptive antenna arrays for GNSS receivers.
Thank you very much for watching and see you next time.
Thank you all for sharing these insights with us today. That was great. We are going to wrap up now. First, I'd like to thank everyone for attending. We appreciate your time. Before we wrap up, I'd like to go over a few closing remarks. Thank you for attending today's webinar, Testing Adaptive Antenna Arrays for GNSS Receivers, brought to you by GPS World Magazine and our sponsor of the event, Rohde Schwarz. If we were not able to answer your questions during the presentation, your questions will be forwarded to the panelists to be addressed via email. If you have any additional questions for myself or our speakers, you can reach out to us directly via the email addresses you see on the slide. A recording of this webinar will be emailed to you tomorrow and posted to gpsworld.com/webinars. Upcoming webinars from GPS World Magazine also will be posted to that page. Thank you all for attending, and we hope you'll join us for another great webinar.